everybody. What we're going to do in this video is cover a double between subjects, or any type of factorial design with all between subjects measures. This one will take a little while because we have a lot of stuff going on, so get ready, let's get started. One of the first things we want to do is just talk about what does it mean to have an interaction. So when we're talking about any type of design with two variable main effects, where I interpret each IV by itself, sort of ignoring everything else, and interactions, where I interpret those IVs together, and I'm looking at if the conditions are significantly different. So I'm looking at the combinations of the levels are different. So I tried to draw a little picture here of what's happening. And let's say we have some sort of, this isn't actually the right picture, this is a follow-up comment here in just a second. But let's say we have like two sets of variables, and in this example I have what year the spending was tested on and what sport. So each IV analyzed separately would be only years. So did I spend more in 2007 or more in 2008? And then each sport analyzed separately. Which sport spent the most money? Now if I'm interested in the interaction, it would be, did one sport spend more money in 2007 than 2008, where another sport did the opposite? So we're seeing if the pattern of effects is different across these conditions. And so instead of being interested in only 2007 or only 2008, I might be interested in the fact that basketball decreased their spending while football increased their spending. So they're in opposite directions. So if I analyze those two things together, you can actually do post hoc tests, what we've been doing for our one-way designs, for each main effect, so IV1 and IV2, and the interaction. And that becomes a lot of work and a lot of tests. So that would be a lot of type 1 error correction going on. You can do it that way. But what often happens is, and I'm kind of here, is that if that interaction is significant, you're really interested in the interaction. Otherwise, why are you doing the analysis with both variables together? Often people ignore the main effects, because then you're running less post hoc tests, so you have a less chance of a type 1 error. So kind of why would you do the interaction if you, why would you have these variables together if you weren't interested in that interaction? Unless there's a very specific hypothesis. So here's kind of a follow-up box, if you will. If your main effect is significant and you do want to follow up and the levels are only 2, which is an example of our spending here, then you just interpret the means. So anytime there's only 2 levels for an ANOVA, a regular ANOVA, which would be a t-test, or a main effect, okay, this is specific to main effects, you just interpret the means. Don't run a t-test on those 2 levels. You've already done that with the ANOVA. You're just repeating yourself. If there's more than 2 levels, just like our ANOVAs that we did in the last couple of videos, you would run an independent t-test, because this is between subjects. You could do Bonferroni, or you could do Tukey if you're working with JASP or SPSS. And that would be true for this main effect. So in our example here, levels here, there's only 2 of them. So if I wanted to analyze that main effect, let's say it's significant, I would find the interaction here, or the intersection, main effect levels equals 2, and I would just interpret those means. Here's the mean for 2007, here's the mean for 2008, end of story. Do not run anything else. However, here I have 1, 2, 3, 4, 5 levels. So I would say levels are more than 2 and significant. Then I would just have to run another test. In JASP, this is pretty easy. The hard part here is the interaction. So if the interaction is significant, we're going to have to split one of the IVs up into different files. And that's going to be the slow part. And then follow up with some sort of t-test or corrected values, which we'll actually have to do a second ANOVA. So we'll have to cheat just a little bit in JASP to get this, which is okay, no big deal. So we're going to start working through this one, just with a warning that it does involve kind of a lot of windows and a lot of kind of flipping back and forth. Okay. So what I'm really interested in is if we look at spending in athletics, which can range to all sorts of crazy, across 2 years' time for 5 different sports, 1, 2, 3, 4, 5, I've never seen that that's a typo. Are there differences in those boards and spending? Well, of course there are. It's fake data. And just in general, our understanding of the way athletics works, at least in the United States, is that there is going to be at least a big difference here with football in the mix. So our dependent variable here is our spending transactions for each individual sport. This is kind of cheat data because it's not really repeated measures, because we're treating each transaction as a separate component, as a separate participant per se. But in theory, right, you're going to have multiple footballs spent. So we're treating transactions as each separate participant in this study, which is a little different, but that's the way we're going to treat these. We'll come back to power and write-ups for this example, and we're going to stick our results, our information that we figure out from JASP down here, just to keep this all in one document. All right, so first thing I'm going to do is do some data screening here in Excel. So let's open this between subjects file. And if you've been watching several of these, you know Excel might crash on us at any moment. And this is a huge data set. So we might have some troubles here getting Excel to give us the residuals, but we'll try because it's got 18,000 lines in it. So it's a very big data set to just kind of show you how to work with small data sets and how to work with big data sets. We're going to do what we've been traditionally doing. So File, Save As. We're just going to save this as a separate file so we can work with it in Excel format rather than CSV format. So this is our data screening file. I'm going to change this to Excel. That'll allow me to work with multiple tabs. So here's our master data set, and let's start working on fixing up any problems that we have. So let's see if we have any typos. Let's work with typos first. And we might not have any. And I don't think we do, but we'll just see if we do. So the first two columns here are our categorical columns. And so I'm going to just look at the accuracy here of those. So I'm cutting and pasting. Control-C, Control-V if you're on a Mac command. And I am going to use the Data tab, or ribbon, and remove duplicates. Now, let's do this one column at a time. But actually, both columns at a time actually is going to be kind of important too. So I'm going to hit remove duplicates, and you'll notice that things are duplicated, but we have each combination. So one problem you might have is if you have what's called an incomplete block design, which means where I have here, so let's say I have 2007, 2008, basketball, football, baseball, soccer, and volleyball. For some reason, you don't have this data. And so that's missing. That would be an incomplete block design. For that, you cannot use between subjects ANOVA because it assumes that you have all possible combinations, all 10, I can't math today, 2 times 5 conditions. And so using both columns at once will actually let me make sure that I have every single possible combination. Additionally, I could just do one column at a time after I've checked that and not click on the wrong button here. Remove duplicates. So I only have those 2. Remove duplicates. I only have these 5. So that's kind of a quick and dirty way to check, make sure you have all of the combinations, because otherwise it won't run. So I would say our categorical pieces look fine. All right, so let's check now on our continuous column. So one thing I've done that's going to be a little different than the R version is that I arbitrarily made this a lot smaller because the first time I tried to record this video, Excel was like, bleh! So the data set is still very large, 6,000 lines. I just kind of made it shorter from the other data set I have, just so this would run better, so you could learn from example and not have to wait 87 years for Excel to calculate the average. All right, that being said, let's check our continuous column. So I'm going to click Data Analysis, Descriptive Stats. I want to do column C here. I got my labels in the first row and summary statistics. I'm going to put this over here, or I'm going to try to see what it says. For some reason, it just doesn't like us doing that. So we'll just tell it to go onto a new worksheet. Not entirely sure why. Okay. This will take a couple of seconds here to calculate because it is still a large data set, even if it's not 18,000 rows. So you might be able to go make a sandwich while you wait. All right, there we go. So, fine, I will stick you right there. So let's look at how this looks. Okay, so it looks like our mean dollar amount spent per transaction was $280 or so. And then I accidentally only made it 5,999 lines, but okay. The minimum is not negative. So remember that the biggest thing with accuracy checking for continuous columns at first is to at least make sure it's not outside the range of the data. So it's not negative and it's not a billion, although I'm sure Alabama might spend a lot of money. I don't think they even hit that sort of range. The numbers here look appropriate, is what I'm saying. So it seems to me like we don't really have any typos. Okay. So since we don't have any typos, I'm just going to kind of move on and call this, let's try no outliers. Or no missing would actually be next. That's where I can cut down on the number of tabs. I don't have a no typos, which should tell me I don't have any typos to fix. Now you can leave them in here and make multiple tabs as much as you'd like, but one thing that you could do as you go is, let's say you do have typos, you might make a little note out to yourself like fixed 4 typos or deleted 3 outliers. And that would be really helpful if you keep the different tabs for when you go to work on writing this up, because that is something that you'll report in the first couple of lines, right? You might also have just an overall sheet to yourself where you keep notes. So kind of whatever system works best for you. Here, I'm going to just move this tab and delete. Never mess with your master one. That's the important thing. But I'm just going to move this tab over, and when I open this up later again and I see that I don't have that tab, that to me means I didn't have any typos. I still checked for them, clearly here, but I didn't have any of them. Okay. Now for missing data, because this is so large, I can't really scroll through it. All the other ones we've looked at, we've just been able to kind of scroll and see. You can also use the little trick where you hit Control and up and Control and down, or Command and up, Command down to find the missing holes. But remember, we can always do Count A, which counts the number of values, highlight everything. In this particular case, for some reason, I did 5,999 lines times 100. Okay, so this value here, remember, is N. And it's that many lines because it is the number of lines here minus the first row. Because the first row is labels. It says I have 100% of my data, so there's nothing to fix. So let's move on from no missing to no outliers. Now, this data set we're probably going to have some outliers, but let's see. So we're going to z-score money. Remember, we're going to hit the equals. I'm going to click on the first data point here. Actually, first I'm going to do is open parentheses. Sorry. Click on the first data point. Minus average. Highlight the whole column. Close parentheses. Close again. So we're doing x minus the mean divided by st, the EV. Open parentheses. Highlight that whole column. Close. And we have to do the double parentheses at the beginning, right, to get it to do the correct order of operations. Hit enter. I'm going to highlight, I'm going to click on this one, go from where it goes from being a white plus to a black plus and hit double click. That's going to take a minute. You might see it say processing. It's usually about right here on both types of computers. I'm going to save this file for when Excel decides to crash. And then let's sort this, since it's very big. You can also use the filter command. I just like sort better. So I'm just going to click here, click A to Z. Now remember that sorts the entire thing, which you want it to do. Don't sort the data and lose your z-scores here. So I don't have any values that are too small. Let's see, but we do have a bunch of values that are too large. And here's the conundrum. With this type of data, I have two options here. I clearly have a bunch of data points that are well above average. So let's see here. And that one's damn close too. So I have like 65 data points that are above a z-score cutoff of 3, which is 0.001. So remember a big important rule. And generally when you have data that is participant fed, meaning the participants gave you the number and we're dealing with people, usually college freshmen, uninterested, sort of like, I do what I want kind of participants, that's when I tend to delete things. Because it looks like people are dicking around and their scores are really wild. When I have this type of data where it's archival, meaning it's not participant fed usually, it's usually something that you've like looked up the numbers for and you know those numbers are real. So I know this amount of money is something they really spent. That's when I'll tend to leave that data in. So I know that the football team really spent this amount of money in one purchase. And so I will not delete these outliers because that data is real. When I'm dealing with participants who are, like I said, usually college freshmen, I know that data could be real. They could be a true outlier in our data set, or it could be them messing around. And so I'll tend to delete them. This is a choice that you get to make. You just have to have a good justification for it. Now on your homework, if you're in my class, I'll tell you what to do so that you end up with the same approximate answers we do. But when it comes to doing real research, you would get to do that choice. So if you were, let's say you're one of my athletic training students, you're testing a sports team, and you have one, let's say basketball player who can jump just extraordinarily high, and everybody else is in the normal range. You were there, you tested that data, you know he wasn't screwing around, he can just jump really high. I might leave that in, just simply because you know the data's real. The outliers become very important when you are not sure if the data is questionable. They also tend to affect mean statistics more than they would other types of statistics, like chi-square, obviously. So another thing that you can do, so you can decide to leave them in because you believe the data is real and you know it is what it is. You can decide to take them out because they're outliers, even if the data is real, or because you're not sure, or you can test it with and without and see what kind of difference it makes to include those outliers. In a very large data set like this, 60 data points is probably not going to make that huge of a difference. If you're working with a data set of only 20 participants, 2 data points might make a large difference. So law of large numbers here, these are going to kind of even out, but I could test it with and without. Okay, it was a really long rant about outliers, but it's a good conversation to have and not always going with they're above 3, take them out. They're above 3, let me think about what that means and what do I believe about my data set, and then make that informed decision. So I'm going to leave this in here as my no out. I'm not actually going to delete any participants, but if I did, or if someone asked me later, well, did you have any outliers? I could say, yes, we tested for it, and there were X number, and I have that data right here. So let us go to our final data set here. And we're going to see just how much Excel can handle when calculating residuals. So fingers crossed this works. So we've covered accuracy, missing data, and outliers. Let's now talk about our assumptions. We're not going to test for additivity, our correlations, because we only have one column here for between subjects ANOVA, so additivity doesn't count. We're going to make a random number here to test our residuals. So equals rand, open close. I'm going to let that fill in. So to test for linearity, normality, and the homogeneity and skedasticity, I'm going to hit data analysis, regression. All right, so under Y here, I'm going to click on my random variable. Under X, I'm going to do money here. And I've left out the labels because for some reason that works better for me. I'm going to tell it to go to a new worksheet to give me standardized residuals, residual plots, and normal probability plots. Now this is probably going to take quite a long time, so if you want to kind of fast forward the video here, that's fine. And we'll hope that my computer does not crash. So I actually paused my recording during this, expecting it to take forever, and it didn't, so hopefully your computer didn't take forever either. All right, so let me highlight this. Remember, we're not gonna look at this stuff. Let's make it this color this time. Black is better, because then I can't see it at all. Okay, what we're really interested in are these two plots and this histogram we're gonna make. And we're gonna have a little bit more fun with these plots today because we have more than 8 points. So to create our histogram, we're going to click Data, Data Analysis, go up to Histogram. I'm going to highlight my standardized residuals. I'm going, for some reason this works, I'm going to tell it to stick that histogram, how about right there, and chart output, so we get the picture. Go OK. Now I found that one thing that Excel is like super fond of doing is sort of creating equal bins. Right? And I've only figured this out just kind of playing around with making these videos for you guys. Is that its favorite thing to do appears to be to create the bins of equal size. So this looks really multimodal or sort of square. So one problem I have with that is that's not really what I care about, right? I'm more interested if they're centered around 0 from 2 to 2. Now it is from 2 to 2, and it's pretty even, but I can't totally tell if that's centered around 0. So another way that we could do this, now you can keep doing it the way that we've been doing it, that's fine, because obviously this chart to me looks like it's pretty even around 0, and that's what I'm mostly interested in. Now I would prefer to see it be a little more normalish, meaning it's tallest around 0 and then sort of tails off. If you want to kind of get a little more sophisticated, I'll actually just leave this one here, is that we can create our own bins, because Excel creates them in this sort of like, I don't even understand what sort of way it creates them. So what I can do is say, let's just make some bins here. And what I want is maybe -2, let's say -1.5. I'm just going to keep going. -1, -0.5. Here, I can make this a little larger so you can visually see it better. I'm also going to hit save. 0, and then the same thing the other way. 0.5, 1, 1.5, and 2. Okay. That would create a nice centered distribution around 0. And I sort of picked those randomly to be between 2 and 2. If they aren't between 2 and 2, it'll give us sort of more on the ends. And that might make me a bit of a better picture. So now what I do is click Data Analysis, Histogram, the same setup we've been doing. This time bin range. Hopefully this works. I looked this up. So I'm going to highlight these bins. And then let's see what happens. Oops, I don't want to overwrite my original. Let us stick it right there. Okay. And this doesn't have to be perfect. Oh no. Undo. Sorry. Come back over here, highlight the actual standardized residuals. Stop being wonky, Excel. Okay. What I want to do right here is tell it to stick just right there. Or whatever happened to my bins. What happened to my bins? Oh, there they are. I want to stick it here next to these bins. Or honestly, just make yourself a new worksheet. It's kind of a lot of work. And hit OK. So now what it did was, and the reason I tried so hard to stick it right there is it created the bins that I told it to create. And it stuck me a graph somewhere. There it is. Come down here, graph. Let me zoom out a little bit. There is a reason for this madness. Give me just 2 seconds to make Excel play along. It's kind of grumpy with me at the moment. So here's our original histogram with the bins that Excel created automatically. Here's me saving. Be sure you save as you go. And then here are my bins that I asked it to do for me. This picture, much easier to see. It's still a bit square, but check it out. It's mostly between 2 and 2. This more here gave me no points, so that point's kind of useless. It is very much centered over 0, and it tails off on the sides. Okay. This is a little bit easier to read, personally, than this other graph. Although it gives us the same information that most of the data, if I can find 0 here, it's right here, is centered around 0 because 0 is here in the middle. And it does, I can't tell that it's tailing off on the sides, but essentially what I did was I took this histogram and I squished it and forced it to have different bins here. And this looks much, much prettier. You can do it either way. I might start doing it this way more often just because it works a little better, and I've realized in making a third or fourth video of this here that this is not the most helpful picture, especially when you look at traditional SPSS pictures that are shaped like this. Okay. All right, all that being said, I would say normality is good, and we already meet the assumption for normality given that we have at least 30 people because we have 6,000 lines. Good grief. Let's drag this one over here so I can make it a little bigger. Oh, I'll be happy when I close Excel. Let's make that bigger here. Look how pretty it is. I don't even need to add the line of best fit on here. It's almost perfectly straight because this is fake data. So I would say that this is linear very clearly. And then our next piece here, which is our residual plot. Now, this residual plot is a bit problematic. It's evenly split this way very nicely. It is not evenly split this way. Right? So with homogeneity, we're going to see what Levine's tells us, because I would say it's fairly evenly spread around 0, which is nice, but it is not so evenly spread this long way. So there is a tail here to this distribution. It looks like sideways brain. And that's not good. That implies that there's different spreads of variances because some of it is spread further out than others. Now when it comes to homoscedasticity, oh, that's nice and square. It's one of the best graphs that you can see. So all that together, that's your data set's okay. You know, it's not great, but it's okay. So it seems to pass most of the assumptions. And then we're going to check Levine's test to look at homogeneity a little better. So I haven't edited the data any, and I'm going to label this right here. Sorry, it's my pen, just so that you guys can look at this again later. And since I haven't edited the data any, I'm going to use my original data set here to import into JASP. So let's close that madness in Excel, okay, and let's go to JASP. I have not tested how big data sets can be handled in JASP, but I haven't heard that there's a limit, so fingers crossed. So let's click on Computer, Browse. Okay, for me, it's going to go to my most recent folder that I've been working in, and this is our Between Subjects 2 ANOVA data. Okay. And I opened that just fine, so we shouldn't have any issues. Okay. So this is a double between subjects. It's still under ANOVA and ANOVA. So that the window isn't changing from our single between subjects, but the number of fixed factors will be. So I'm going to put money here in my dependent variable, both year and type in my fixed factors. Remember, we're not doing weighted least squares. Under, sorry, wrong button. Under assumption checks, I can ask for Levine's test. And so Levine's test tests all the groups as if they were separate entities. So it tests each condition against each other, because that would be the combination of interactions here. And it is significant. Okay. So it's less than 0, 0, 1 here. So you see the little less than sign. So that would say that is significantly bad. So I would argue here that we'd have to maybe do something else on our ANOVA. So there are some options where you could change, if you don't want to change those, to a Welch correction, which is really for one way between subjects. If you wanted to fix this ANOVA for homogeneity, you would have to do it in another program. But there are ways that we could test this in a non-parametric style. Okay. However, right now, the point is to talk about between subjects ANOVAs. So I just want to show you one that was significant. So here, this is significantly different variances. Okay. So it matches that homogeneity chart that we saw where it didn't have an even spread across X. But as per usual, when I say, well, there are other ways to do this, but here we go, we're still testing between subjects. This is a common theme where I can show you things that are going wrong, but for the purview of this class, we're going to keep going, because hopefully your variances won't be too crazy. What I want to do now is I can work through a bunch of different options. So I've got my analysis here that we've already run. And then let's click on additional options down here and ask for effect size. So I can look at my eta squared values. Now let me interpret this ANOVA to decide where we go next. Okay. Let me also ask for descriptive stats. That's going to be important. So the nice thing about the descriptive stats is that it breaks it down by condition. Okay. If I were to use descriptives in this window, it would only really just give me the descriptives of money overall. This actually shows me the differences in means based on which group they're in, each condition they're in, right? So the combination here. If I wanted to know just years means and just types means, I would ask for it here. So remember, this is give me standard error instead of standard deviation, but that's okay. Now I have just 2007 versus 2008, and it looks like the mean money spent is dropping. And then I have each sport. And so I could say, well, looks like basketball is actually spending the least amount of money, which is a little, I would say is a little unusual, and football is spending the most amount of money. And then the same marginal means here appear down here, this time with standard error instead of standard deviation. But these end values are going to be really important here in a minute. So scrolling back up, what happened in my ANOVA? I already know my Levine's test is significant, but barring that, what happened? Well, my year variable was significant. So there's a significant difference in the amount of money spent by year. And that is, this is an example I wanted to show you about power. So we have a crap ton of people, which at a specific end value, everything is significant. Because look at this eta squared here. It's very small, 0.002. So that implies that this effect is very, very small, although it is significant. And so if I come down here and I look at my marginal means, so the means just for year, it's about 20 bucks. Do I really think that that is an important difference? So they've reduced their spending about $20. I guess it's almost 10%, so it kind of depends on if we're talking about, if we're talking to the athletic director about reducing money, right? But I would say this effect overall is small. So this is another reason why I've spent so much time harping on effect sizes, because it is significant, but practically we have to decide if that's an important amount for us or not. Now, there's also clearly a difference across the sport. I have it labeled as type, I don't know why. Sport. And I could test if these differences, which ones were significantly different. Okay. If I wanted to do that, so here under year, I didn't do anything else, right? Because it only had 2 levels. But if I wanted to test the marginal means, what I could do is click post hoc test, pick type, move that over, and 2 key, remember, is our favorite option. And this would compare every type to every other type. And they're all significant, mostly because the n values are so large. And I would have to determine the effect sizes to determine if that was practically important. Now for me, I don't know. I know those different sports are going to spend different amounts of money, right? Because, I mean, their equipments are just different costs. There's just more things that you need from one sport for another. So I don't know if I'm interested in this so much. But that's how I would do it if I wanted to. And then I would go through each one and calculate D. Here, the interaction is also significant. Now, practically eta squared wise, this is just not really that important, right? But for purposes of demonstration, it is significant. And I'm going to analyze the interaction so that you can see how to do interactions for when they are big effects and you are really interested in them. Okay. So our interaction is significant. Actually, all three are significant, mostly driven by sample size. And even though this effect size isn't very large, I'm going to follow this up just so you can see how to do these things. Okay. Now, excuse me. With this sort of design, there's 2 different ways that we can analyze this. And I lovingly call this across or down. This is a very technical term, across or down. And what I mean by that is, I'm going to go to Word here. We can analyze going across one variable or down another. So here we have years. So let's say 2007, 2008. And here I have sports. I've got basketball, baseball, I don't think I'm doing this in order, but you get the idea, soccer, volleyball. I typed my brother's name because he played soccer, which was kind of fun there for a second. Just a weird Freudian moment. Now what I mean by across or down is I could analyze, so there are means in each one of these, right? So each one of these is a condition. 2007's basketball money and 2008's football money. Instead of a level. The level is basketball, ignoring year. The condition is the combination. So what I could do is analyze for basketball. I could compare 2007 versus 2008. And then do that exact same thing for football and baseball and soccer and volleyball. So essentially, that would be 5 comparisons. Oop, not volleyball. Good grief. Okay. And so that way I would be comparing down. So are we going down each column? Now, across or down depends on which way you write this out, but it's just a good way to think about it. If I was going to go across, what I would do is for 2007, I would have to then analyze, I'm just going to abbreviate here, basket versus baseball, basket versus football, basket versus soccer, basket versus volleyball. Oh my gosh, it keeps going. Now we would need to do baseball versus football and baseball versus soccer. You can see how this is going to be a bad idea, right? Baseball versus volleyball. Oh wait, still more. Football versus soccer. Football versus volleyball. And then last but not least, soccer versus volleyball. And that should be 10 comparisons. Wait, let me just number these. Okay. But that's not it. We then have to do the exact same thing for 2008. So in sum total, down here is 5 comparisons. Across here is 20. That's a lot. 20 is a lot. And so what should we do? Because this is kind of insane here. The difference is 5 comparisons versus 20. Now, if you have what's called a square design, a 2 by 2, 3 by 3, 4 by 4, where there's an even number of levels in each group. Across or down doesn't matter. Go with whichever way makes more sense that you can explain, or whichever way your hypothesis is. So kind of what are the rules for across or down? Oh, spelling. Split by the larger variable. Okay. Actually, the first rule is always go with the hypothesis. Or if you're a student, do what your advisor wants, because that's how you graduate. Or go with the hypothesis. And I've taken these rules from Keppel and Wickens. So if the hypothesis was to analyze by year, you're stuck with going by year. But in this example, I don't really have a specific hypothesis. So what I would do is split by the larger variable and analyze by the smaller one. Okay. What does that mean? By split, I mean do the 4 part. So I would split basketball into one group, baseball into football, soccer, and volleyball into one group, and then just do the comparisons in the smaller groups. Because that will always make smaller number of comparisons. Okay. And that's why. So why is that a good thing? Okay, so that's less type 1 error. That's why that's a good thing. So that's what we're going to do, is we're going to split by the larger variable, and that's what you should do in all of the assignments that I give you, because there might not be a specific hypothesis per se. If it's a square design, pardon me, pick one. Pick the one that makes the most sense to you. Now, what do I mean by split? Unfortunately, this is one thing that I think SPSS does better than JASP, where you can sort of fake split file and then analyze this all in one window. We're not going to be able to do that. We're going to have to do this a little bit manually. And so let's make sure there's nothing else that we need at the moment. So we could make some plots, but we've already talked about how we don't really like the plots in here too much because they're not editable. So I'm going to save this output. Okay, so I'm going to just go ahead and stick the ANOVA output here in the Word file because I'm going to need it again in a minute. See if we can get that to not paste so ugly. There we go. Now what I'm going to have to do is the kind of what I would say slow part, although data screening is kind of slow as well. And I'm going to have to split those files and separate them myself. Okay. Okay, let me hit save because it's kind of freaking out. And we're going to have to do this a couple of times. So I'm done with this particular JASP file because I can't do any more with my main data set here. Okay. There's no good way to tell it to select only 2 of the types and then hit t-test and do independent t, because that's really what we're wanting to do here. Unfortunately, there's no way to do that. Okay. So I'm going to close out this one, and I'm going to go back to Excel. And from here, I'm going to create myself new files. I'm going to copy my original Excel file, hit V, and we're going to call this one basketball for basketball. I'm going to do that a couple times, mostly 5. I'm just going to make new files for each one. I'm just base. Okay, volleyball, football, and soccer. Okay. So now I've got data sets for each one of my files. Okay. So I'm open it up, and I'm going to delete all the other rows. So this first file is for baseball. And so what you can do instead of searching, because this is a very big data set, and so searching for every other column that isn't baseball is going to be a little bit of work. So we're going to use the filter command. Okay, it's under data, click up here somewhere and click Filter. Click the little drop down arrow and deselect the one you want to stay. I know this seems backwards, you'll see why in a second. So I'm going to deselect baseball here. Close this. Now I'm going to highlight everything else. And so I am doing that by doing Shift, Control, and then using my arrows. Or if you're on a Mac, Shift, Command. I'm just going to hit delete. Okay, that's kind of a scary thing to do because then it all goes away. But if I turn off filter, our baseball stuff is there at the bottom. So I can just kind of hit sort to bring it to the top. Whoops, I cannot do that. I can hit this version of sort. Tell it my list has headers. Sort by the first column. Okay. And that'll just bring it to the top. So now I've deleted all the lines that weren't baseball. I've hit save. I'm going to close this. Now, anytime you try to close a CSV, I hit save, hit Control S. It says, are you sure do you want to save the changes? And it makes it kind of sound like you haven't saved, which I don't know why Excel does this. I'm going to hit don't save, which is kind of also scary. But you'll see that my baseball data set only still has baseball in it. So it's saving, and then it's just decided that it's something about CSV files. Right, now I'm going to open up basketball and do the exact same thing. So I'm going to do this 3 or 4 times to get rid of all of the other data. So you will want to do that with me. So click Filter, deselect basketball because it's the one I want to keep. Highlight everything, erase, turn off filter. This one's at the top already. And the only reason I tell you to bring the data to the top is so that you don't have all these weird blank lines. Hit save, close, don't care. Let's do the same thing 3 more times. Filter, deselecting football here. Turning off filter, I'm going to highlight all 3, hit A to Z sort this one, sort by column A, sure why not. My list has headers, just so it doesn't put the year thing in the middle somewhere. Save, close. Do the same thing here for soccer. So data, filter, deselect soccer. Highlight everything else, hit delete, turn off that filter, A to Z sort, column A, my list has headers, save. If you aren't, oops, don't hit paste, good grief. If you aren't good with Control S, Control V, you will be by the end of the semester, but you can also do file save. Don't save. One more time. Here's volleyball. Okay. Filter, deselect volleyball. Delete. Turn off the filter. A to Z sort. Last time, yay! Perfect. Go away. Now, what we're going to do is 5 different JASPs. Okay, this should go a little faster. But the first thing I'm going to do is create that post hoc table that we have been working on before. So we did this last time. We did group 1, group 2. Okay. We talked about the comparison. And then we talked about coincidence. All right, so we were making this comparison chart to be able to tell whether or not these were significant comparisons. So I'm actually going to add one more column here to the right. And what this is going to be is our split group. So this is the analysis we had done before, but now we're going to have it split up by basketball, baseball, football, soccer, and volleyball. And then the comparison for each one of these is 2007 versus 2008. So you'll see how we have conditions here. Instead of levels, you know, we're only comparing 2007 to 2008 or basketball to baseball. We've got for each condition we're doing a comparison, right? And so we could take our descriptives that we have here that are split by those comparisons and type those in. And so that's going to take me a minute here, but we can also run the JASP analysis at the same time. So we're going to want the mean and the standard deviation. Good grief, computer. I even gave it a break. And n for each one. And that's important because we'll have to be able to get the d values. And we'll need all of those numbers for Cohen's d. So yes, it takes a little bit to do this table, but then you have it at least all in one place, and you can also cut and paste a lot of this stuff into Excel. All right, so let's start with basketball. So I'm going to reopen JASP. And this time I'm going to open the basketball only file. And so I'm going to open, did I do basketball first? I did basketball first. And make sure it just says basketball here. So we're going to go t-tests, independent samples, because this is between subjects design. We're only going to put in year, because we split by type of sport. Put money in the dependent variable here. And then we want to make sure we get that effect size with it. We can also add our descriptives just to make sure they match the ones that we should already be getting. And so here's our output for basketball, which we can save here after the table. Oops. As you guys will learn, spelling not my forte. So I had that the mean is 197 for 2007. Let's just make sure that matches what we have up here. Yes. Okay, so here's the mean standard deviation and n for 2007 that we're interested in. So if I wanted to, I guess I could just cut and paste like this. Oops. Or not. Let's see if we can get it to paste in a way that's, nope, it's pretty grumpy. Okay. So we would just want to type those in. Okay, so it's 197.6, 121.3, and 1866. Now for 2008, it's 222. Oh, make sure I look at the right line here. 185.3, 112.4, and 1677. Now this is only one comparison, right? So there's no real reason to correct here, because when doing it this way, we would have to do a corrections manually ourselves. But there's just there's only one comparison, so there's no real correction to be had. Generally, people won't tend to correct if you're doing this number of small tests. If you wanted to, you could do Bonferroni manually, where I could compare my p-value to a new criteria, and that's what we'll kind of talk about here. So what I'm going to do is I'm going to type my t-test values and my Cohen's d into our comparison over here. So let's move this over here. So I'm going to type in T, this is APA style, right, is our degrees of freedom are 3, 5, 4, 1. Silly word in its auto capitalization. P-value equals 0.002. And D over here for independent T equals 0.10. And so that's a very small effect. Remembering that 0.2 is generally considered a small effect. So this is a small effect. Do we think this is important that they've decreased their spending $12? Maybe, but probably not. So we want to do this exact same thing 5 times, once for each sport. So let's do one more sport, and then I'll take a pause and I will do the rest of them, and we'll talk about how to interpret this, just so you don't have to sit here and watch me open and close 5 files. So we'll do this exact same thing one more time. 5 more times, or 4 more times, because we've done 1 and there's 4 groups, 5 groups. Oh my gosh, we've done 1 of them of the 5 groups, which means there are 4 more tries. So let me open baseball this time. I'd click t-test, independent samples t-test. Remember, we're comparing by year. Put money in our dependent variable here. Click on effect size. And then now I have the effects for this one, and I could also ask for the descriptives just to make sure they match. So I would copy these results, come over here to Word. Okay, my basketball ones didn't copy, or I didn't paste it because I got distracted. So let's paste that in here. Let me go back over here to basketball, copy, paste that here. All right, so I would copy this t-test information into my little table here along with all the means. So for baseball, if we zoom out just a touch, scroll up here, we've got 235.6. The standard deviation is 153. And in here is 1619. For 2008, we've got 222.7, 147.7, and 1483. Our t-test values from JASP are 2.39 with 3100 degrees of freedom. This one is significant as well. Goes 2.39. P equals, let's go back down here, 0.017. Cohen's D was 0.09. Oops, 17. And I'm going to do all 3 decimals here for a reason. Oops. Equals. There we go. All right. So I'm going to take a quick break. I'm going to fill in the rest of this chart. You should try it on your own. Try running football, soccer, and volleyball by yourself. See if you get the same answers that I do. So kind of pause the video here and see if you get the same numbers when I come back. And we will talk about how can I do a correction on this sort of thing and then keep going. All right. So you should have paused and gone through and tried the other 3. And so you should have gotten approximately these values. where football dropped about $37. Its t-value is significant with a small effect size. Soccer only dropped about $20, significant with a small effect. Volleyball also $13, significant, very small effect. Okay. And I've pasted all of the results down here at the bottom so that you can look and make sure yours matches mine. So we've gone through all this trouble and we've made this huge chart. And really what we've done is we figured out a way to analyze interactions in JASP. So it is a bit of work because you have to split the files up. And this is a big example to kind of show you, going through the steps and the motions of each particular file. And I've also calculated all the effect sizes. So the nice thing is, in one way between subjects and ANOVAs, it gave us the chart, but we had to use another program to calculate the effect sizes, our moat program. But in this example, we were able to get those effect sizes directly from JASP, which is kind of nice. Now, one problem with this table is there's no correction on this table. Okay, so no correction for type 1 error. We've only run independent t. Let my computer catch up here. It's struggling with how long this is. So we've only run independent t. So what do I do to correct? And the easiest thing in this scenario is to use a Bonferroni correction. And it won't actually correct anything, but we could look at our new p-values. So to do Bonferroni, I think it's 2 R's and 1 N. I'm never sure. Sometimes I spell it with like 8 R's and 6 N's because I can never remember. What we want to do is take alpha and divide by the number of comparisons. And what that is a new criterion. So we're going to make that criterion 0.05 divided by the number of comparisons. Well, in this case, there's 5, 1 for each sport. And so our new alpha, or criterion, is, thankfully, easy math, 0.01. Okay. So if our found p is less than 0.01, then it's significant. Ooh, I don't know what I was trying to type here. Signification. There we go. Then it's significant. So in this particular case, that's less than 0.01, so I would say this is significant. Traditionally, this would be considered significant, but if we correct, we would say it's not significant. Okay. This one would be significant. Okay. This one was not, because 0.017 is not less than 0.01. If you struggle with decimals, multiply everything by 100. So it has to be less than 1. So if I move the decimal over 2 points here, that's less than 1. If I move it over 2 points here, it's 1.7. This one would be significant. And this last one would not be significant. And that's just if you want to correct. So traditionally, when I have a very small number of comparisons here, given the size of this design, a 2x5 design is big. I don't know that I would correct these. But remember, I've talked all semester about how I don't think that p is super useful, right? Because it depends on the sample size. These p-values are significant because look how big the sample is. And that doesn't tell me a whole lot. It tells me in this sample it's significant because I have a lot of power. What I'm going to focus on really more so than being too concerned with corrections, although they are important, I'm not saying that, they aren't, is the effect sizes here. So all of these effect sizes are very small. And I would say that matches what we found at the very beginning of this video, in that the overall ANOVA's effect size is also very small. And so those two things will go together. And so here, I would say that none of these are really significant, like practically very big differences. $10 to $12 across many of the purchases might add up to a lot. So it might be practically useful for the program trying to save money. But if I was looking at these and let's say a drug study, I would say these are not very helpful numbers. Now, another question that I often get asked is that the interaction. I don't understand this interaction, because we talked about interactions being different patterns of results, and every group is going down. And so that'll happen where you don't have one group that's going up and one group that's going down. That's a good interaction because one's going up, one's going down. Here, the problem is that they're all going down. So what the hell does that mean? So the reason that you're getting an interaction effect is because the D values are different. So when the direction is the same for all of them, they're all going up or they're all going down, the way to tell that this is an interaction is that they have different effect sizes. So they're going up and down at different rates. They're all going down at different rates or they're all going up at different rates. And really the best way to see this is to make a graph, which we will do here in just a second. One thing I know I skipped a minute ago, and I didn't mean to, or more than several minutes ago, is how to write this up. I know we've practiced this before, but I know it won't hurt to see it again. So if I'm going to write up Levine's test here, just going to move that box out of the way, I would say Levine's is significant. And then we might talk about corrections. But with such a large sample size, I don't know that it's really necessary. Because remember, if you have a significant homogeneity problem or heterogeneity, it often is a loss of power. So we're going to report this as F of 9 and 18250, okay, which is these two numbers here. And then we're going to report F here. So 266.5, and then our p-value. So that's how we would report Levine's. Now with our ANOVA test, what we've got is 3 different F values. And one temptation, although it's not the case here, is to only talk about the significant ones, which is what you shouldn't do. Okay, so when you have an overall ANOVA like this, you should report all of the effects, even if they're not significant. And that's true of post hocs as well. If you ran the post hoc, you should report it, even if it's not significant. So we would talk about there being a significant effect of year, and we would write that up as F. Now year here is 1 degree of freedom here, and 18,250, this number, which will be repeated a couple of times. So 1 and that 18,250. F is right here, so 4929. Our p-value is less than 0.001. So actually cut and paste that bad boy. And then eta squared here, so paste that so I don't have to find the eta symbol. Italics is equal to 0.002. Now eta doesn't get bigger than 1, so I'm going to leave the trailing zeros off of both of those, or the first zeros. All right, now type is also significant. I'm just going to paste the whole thing to make my life a little easier, but the degrees of freedom here are 4 this time, because it's groups minus 1, and we have 5 types of sports, or 5 sports minus 1. Here it was number of years minus 1. Okay. And our F value is here. Since I cannot type today and my computer is struggling to keep up with me, my eta squared value here, this is definitely the largest effect. So it's about somewhere between a medium and a large effect, depending on which sizes you go with. And then the interaction is also significant. Okay, so we're going to copy this, paste this. So it's also 4 and 18,250. Our interaction's kind of small though, so 3.47. P-value is 0.008. And our eta squared is 0.001. And you would want to report all three of these. So when you look at the write-up here, the write-up example, which is closer to the top here, what I've got is I first talk about what I'm doing and all the different levels that are considered. Talk about the screening for assumptions, so that Levine's test is bad. It says that large sample size is going to influence that factor. And then I talk about my high standardized z-scores. Okay, so there are several things that were considered outliers, but in our example, we didn't exclude them. I did in this example. I talk about the type of ANOVA that I ran, a 2x5 between subjects ANOVA would be better, because that would indicate that both variables are between subjects. Talk about the main effective year, the type of sport, okay. The interaction, and in this particular example, it was not significant. In our example, it is significant. Okay. And then we're gonna talk about the interaction here. So independent t-test with Bonferroni correction. And then we would talk about and use all of our t-values. So we talk about each one separately. So you'll notice, and I'll clean this up a little bit to have our numbers, that we'll talk about Levine's, talk about all three F's, 1, 2, 3, and then all of the post hoc tests. So we'd have 5 listed here. And then last, we would create a figure. Okay, so we've got everything going on except our figure. And I think I must have split file on the original data set with 1,800 people, is what it's looking like. Let's check that out real quick. So we might have data screened one data set and run another data set, which is an absolute no-no. I don't know. It doesn't look like it. Let's check it out. Yes. So we data screened one set and ran the analysis on another one, which you shouldn't do. Don't do that. But I'm going to leave it like it is so that you can match your numbers to mine in this video. Because what I did was I made the data screening shorter by cutting out a bunch of the data points, but then forgot to do that in the original data set, which is my fault. But so that you get the same values that I'm getting in the video, I'm going to leave it. Just as an aside, that shouldn't happen because you shouldn't be the instructor cutting out the data points in the middle. Okay. So sitting there wondering why our degrees of freedom were so large, because our data set should only have 6,000 participants in it, but that's my fault. Okay. All right, so what we're going to do now is make our figure. Okay, so let's go back to Excel. And now we're going to make a double bar graph. So we haven't done one of those since the graphs video, so I'm going to go down and find our marginal means here. That's our post hoc box. Let's find our descriptives here. And I'm going to cheat, cut and paste them. Let's see if we can get this to cut and paste correctly. Close enough. We're going to take this column here, put that here. Let's kind of move things around a little bit. So here are our means. Okay, and you don't have to really stick this in C7. You know, I just like to stick things in a slightly different place since I'm just making a graph. Now let's also include standard deviations. And this is 2007, 2008. So our standard deviations are here. And then here. And what we want to do to make this graph is highlight everything here. Click on Insert, Cluster Bar or Cluster Column Graph. And then we've got this graph. So which way should I do the graph? Should I do the graph this way? Or I can switch row and column and do the graph this way. So 1 or 2. And what I always tell people is to make the graph in the way that you did the comparisons. So I split on this variable so that now these two comparisons are next to each other. So what that means is my t-test is these two compared to each other, these two compared to each other, and these two, etc. So I'm going to leave the graph this way because these are the comparisons that I made, not these. So if I had split on year and compared them within each year cluster, I would do it like this. And that's just a personal thing because I think it elucidates the data, meaning that it shows you the comparisons that you made and not, and you don't have to struggle quite as hard to go from the t-test to the chart. All right, so let's clean this thing up a little bit. We're going to add axis titles, both vertical and horizontal. Now that I have all of the words on the chart here, I'm going to click on the chart, change the font to Times New Roman. We're going to change this axis title to Sport, Sport, there we go. Change this one here to Average Transaction Spent. Okay. So something more descriptive than just the word money. Take my legend, put it up here in the top. We're going to have to be careful doing that because of our error bars here in a minute. So we might, end up moving this around a little bit. Go. And now let's add our error bar. So I'm going to click here, Chart Design, Add Chart Element, Error Bars, More Options, Custom, Specify, and now start highlighting. So these go down. Highlight the same thing twice. Remember, you want these two to be the same. Hit OK. Click here. Now the reason I knew that it went down was because I looked at how it was highlighted here. Chart element, error bars, more options, custom, specify, highlight, click, highlight, click. Oops, I think I did that wrong. Yes, so they're not the same. Did not do that on purpose. So don't highlight your means again. Okay. So our two error bars and look they're the same. Hit OK. Close this for a second. And that's actually looking pretty good. So our error bars are not overlapping our legend, because that would be bad. I don't really love that this is blue and orange, so I might be able to make it monochromatic here, just so it's a little bit more printable. Copy that. Paste that into Word here. So if we weren't having enough struggles already in this video, the cats are trying to help now. Go back to... Okay, so remember how it likes to change colors on you. So I'm gonna hit Control Z, Control V one more time, and you get this little square bracket thing here. Keep source formatting. There we go. It also helpfully added that line around it, just because why not? So what we want to do is click Format when we clicked on the chart. Here, no outline. There we go. And this is an appropriate graph. Oh, I didn't draw the bar lines. Doh. Just kidding. So the other thing I want to add is the axis lines. So I double clicked on the axis to get that. Click on this thing, paint bucket here. Click line. solid. Remember, you have to make it black. We're going to do the same thing for the other one, solid and black. Okay, and that looks better. And the nice thing about pasting it is it should be linked to the one in Excel, but sometimes that doesn't always work. So I'm going to go back, copy this one, paste this into Excel. Come on now, keep source formatting. And we're going to get rid of that border again. Click Format. No outline. All right, so although we've struggled a little, we've gone all the way through data screening on the shortened data set, which was accuracy, missing, outliers, our assumptions of normality, linearity, homogeneity, and homoscedasticity. Our homogeneity was a bit messy, and so we looked at Levine's test, which also showed that it was significant. We ran the entire analysis. I talked about how to write up Levine's and the ANOVA towards the end. We talked about the complicated thing that is post hoc, so having to split the file, usually on the larger factor, so create more files than you need, so you can run the smaller number of tests. We got our effect size. We talked about how you can correct, even though it doesn't do it for you automatically. We've covered just now graphs, a little bit of the write-ups. So we have one last thing, which is power. So I'm going to open GPower. And this is at the very top of this document as well. So I'm going to click Test Family, go to F-Test. Here under Statistical Test, I'm going to choose ANOVA, Fixed Effects, Special, Main Effects, and Interactions, because it's more than a one-way test. Under Effect Size F, I'm going to hit Determine. And we had a very small effect size, so we're going to enter that one. So 0.001. Calculate and transfer to main. Our alpha was 0.05. Power is 0.8. Those don't change. Our numerator degrees of freedom, and this is where it changes depending on what you're interested in. So come down over here. If you're interested in only the main effects, you'll do levels -1. If you're interested in the interactions, you'd do levels -1 times levels -1. So we would do 2 minus 1, 1, times 5 minus 1, 4. 4 times 1 is 4. Generally, you're going to go with the interactions because that's the purpose of this design. So we're going to say there's 4 here. The number of groups depends again on what you're interested in. So if it's for main effects, it's the number of levels. If it's for interactions, it's the number of conditions. So 2 times 5, which is 10. And hit calculate. Okay. So it says that we actually need 11 or almost 12,000 participants. If we had gone with that original 6,000 that we had, it probably wouldn't have turned out significant. In this example, I picked a medium effect size, 0.09, so you can try that one on your own. And I would only need 126 people, so that's the difference that power makes. The larger the effect size, the smaller the sample. But if we went with our original effect size, we would need 11,000 participants, which wouldn't normally be practical. So that's how you can calculate power for a double between subjects design. Please let me know if you have questions on any of the pieces that we've covered here. If you are in my class, I'll have all of these files kind of marked out for you so you know which ones I used when, so you can follow along.